Imagine a blueprint, a complex, intricate design. Lines for qubits, the fundamental units of quantum information, gates for operations, the instructions that manipulate these qubits. This is a quantum circuit, the language of quantum computers, a new way to communicate with machines. It's a dance of probabilities and wave functions, a realm where things aren't just 0 or 1, but exist in a superposition of states. Now the circuit morphs. Gates become nodes, lines become pathways representing connections and weights, and suddenly it resembles a neural network, a familiar structure in the world of artificial intelligence. The core of AI, the engine that drives learning and decision-making. This isn't just a visual trick, it's more than just a superficial similarity. It's a metaphor for a new frontier, a convergence of two powerful fields. Quantum computing fused with machine learning, creating a new paradigm of computation. The strange rules of the quantum world, the principles that govern the behavior of matter at the atomic and subatomic levels, superposition, entanglement, once considered purely theoretical concepts, are now tools for building machines that learn and reason, pushing the boundaries of what's achievable, in ways once thought impossible, unlocking new possibilities in artificial intelligence. This convergence promises computational power on an unprecedented scale, far beyond the capabilities of classical computers. Quantum computers don't just make things faster, they offer a fundamentally different approach to problem solving. They change how we process information, opening doors to new algorithms and solutions. The first generation of quantum processors is already here, marking the beginning of this exciting era. And researchers are building quantum machine learning models today, exploring the potential of this technology. We'll explore the basics, the building blocks of quantum computation, qubits, variational circuits, the algorithms that harness the power of quantum mechanics, and hybrid models where classical and quantum processors work together, combining the best of both worlds. We'll also face the challenges ahead, like quantum noise, a major hurdle in building reliable quantum computers. This is a story of human ingenuity pushing the limits of what's possible, venturing into the unknown. The journey begins with a single, strange bit of information, a qubit, the quantum equivalent of a classical bit. Welcome to the dawn of quantum machine learning, a new era of intelligent machines. Let's see how the quantum world is reshaping intelligence, transforming the way we think about computation. The future starts now. To understand quantum AI, we need to start with the fundamental building block, the qubit. It's the cornerstone upon which all quantum computations are built. The qubit, the quantum version of a bit. Unlike a classical bit, which is limited to representing either 0 or 1, a qubit can exist in both states simultaneously, thanks to the mind-bending principle of superposition. Picture a spinning coin, suspended in midair. While it's spinning in the air, it's neither definitively heads nor tails, it's both at the same time. A qubit operates in a similar way. It exists in multiple states, a combination of 0 and 1, until the moment it's measured, at which point it collapses into a single definite state. This ability to exist in multiple states at once means that a single qubit can hold significantly more information than a classical bit. And here's where things get really interesting. As you add more qubits to a quantum computer, the computational possibilities grow exponentially, unlocking immense processing power. With just a few hundred qubits, you could potentially represent more states than there are atoms in the observable universe. Superposition empowers quantum computers to explore and process countless possibilities simultaneously, a concept known as quantum parallelism. The second key principle is entanglement. When qubits become entangled, their fates are intertwined. Their states are inextricably linked, regardless of the physical distance separating them. If you measure the state of one entangled qubit, you instantly and definitively know the state of the other, its entangled partner. This phenomenon so perplexed Albert Einstein that he famously referred to it as spooky action at a distance. Entanglement gives rise to complex correlations between qubits, correlations that classical computers struggle and often fail to efficiently simulate. Together, the principles of superposition and entanglement form the very bedrock of quantum computing. They empower quantum algorithms to tackle computational problems that are simply intractable for even the most powerful classical computers. These are the fundamental rules that govern this new and revolutionary computational paradigm. And it is upon this strange, yet incredibly powerful foundation, that the field of quantum machine learning is being built. So, let's delve deeper and explore how these quantum principles are poised to unlock a whole new realm of possibilities in artificial intelligence. Quantum computers aren't just faster versions of classical ones. They represent a paradigm shift in computation. They excel at specific problems that are intractable for even the most powerful supercomputers we have today. The real advantage is in how they scale. The power of quantum computing grows exponentially with each added qubit. For some problems that take classical computers exponential time, rendering them practically unsolvable, can be solved much faster with quantum algorithms. This opens up possibilities previously confined to the realm of theoretical computation. For example, consider the task of searching an unsorted database. Classically, using a standard linear search, you'd have to check, on average, half the entries to find what you're looking for. Quantumly, Grover's algorithm achieves the same result in the square root of the number of steps. That's a huge speed-up, especially for large databases. Even more dramatic is the problem of factoring large numbers, a cornerstone of modern cryptography. Classically, with the best-known algorithms, factoring very large numbers could take longer than the age of the universe. But Shor's algorithm running on a quantum computer can accomplish this feat in polynomial time. This exponential gap is precisely why quantum computers pose a significant threat to current encryption methods, and conversely promise groundbreaking advancements in scientific simulation, allowing us to model complex systems with unprecedented accuracy. Many AI tasks like optimization and sampling, which are crucial for training sophisticated models, become intractable for classical machines as the amount of data grows exponentially. Quantum algorithms operate in high-dimensional spaces, far beyond what classical computers can effectively manage. They are leveraging the principles of superposition and entanglement to navigate this complexity and find solutions. The central goal of quantum machine learning is to identify and harness these problems, where this exponential speed-up transforms the impossible into the manageable, unlocking new frontiers in AI. It's not simply about making existing processes run a little faster, it's about making the previously unthinkable computationally possible. Quantum leaps redefine the very boundaries of what's computationally achievable. The future of AI, and indeed many other fields, may very well depend on these quantum leaps. Let's explore how these quantum algorithms are poised to revolutionize the landscape of artificial intelligence. How do we use quantum computers for machine learning today? Two leading approaches: variational quantum circuits and quantum kernels. Variational circuits are like quantum neural network layers with tunable parameters. Data is encoded, processed, and the parameters are trained using a classical optimizer. This hybrid loop, quantum processing, classical optimization, gradually improves performance. Quantum kernel methods enhance classical support vector machines by mapping data into vast quantum state spaces. The quantum computer estimates similarities between data points in this high-dimensional space, potentially revealing patterns classical computers can't find. These methods let us harness quantum power even on today's noisy, small-scale devices. The synergy of quantum and classical is already reshaping machine learning. The revolution has begun. Beyond basics, new quantum algorithms mirror classical machine learning goals. The Quantum Approximate Optimization Algorithm, QAOA, tackles tough optimization problems, like finding the best route or portfolio, by evolving quantum states with tunable parameters. It's a hybrid approach using quantum circuits and classical optimization to find high-quality solutions. Quantum neural networks, QNNs, go further, replacing classical network layers with quantum circuits. Data flows through quantum subroutines, enabling transformations and learning patterns impossible for classical networks. Some models use quantum circuits at the input, others intersperse them throughout. The aim leverage quantum phenomena directly in learning, creating models that are not just faster but fundamentally more expressive. Quantum AI is pushing the boundaries of what machines can learn. Today's quantum machine learning is a powerful partnership. It's not a replacement but rather an augmentation. The hybrid workflow, classical computers handle the crucial data prep and optimization stages. Meanwhile, quantum processors tackle the computationally hard calculations. Quantum devices are still relatively small and noisy. Therefore, this division of labor is absolutely essential. A typical iterative loop, the classical computer sets up the problem and defines parameters. Then, it sends them to the quantum processor. The quantum processor runs the circuit and returns results. Measurements are repeated many times to build up reliable statistics. The classical optimizer then updates parameters and the cycle repeats itself. This iterative loop is the very heart of near-term quantum machine learning. By combining our strengths, we unlock exciting new computational possibilities. Quantum computing's power comes with fragility. Qubits are sensitive and quantum states easily disturbed by noise. Decoherence and errors threaten computations, making large-scale, fault-tolerant quantum computers a major challenge. Quantum error correction is the ultimate solution, but it requires many physical qubits and is still experimental. For now, error mitigation techniques help. Zero-noise extrapolation runs circuits at different noise levels and estimates the ideal result. Other methods, like probabilistic error cancellation and dynamical decoupling, further reduce noise effects. These techniques are vital for extracting useful results from today's hardware. Overcoming noise is the central quest for quantum AI. Success will unlock breakthroughs in fields from drug discovery to finance. The future of computation depends on taming quantum noise. The quest for reliable quantum AI is just beginning.